Alright, so this will be a very quick video to show you some assorted problems for what is normally the last test in Calculus 1. Alright, so I'll go through them fairly quickly, show you the question, show you the answer, and for some of the work in between I might explain a little bit, but by the time we've gotten to this point, I've explained most of the details of these types of problems in other videos. So just going to go through it real quick. So first question, straightforward antiderivative, the type where you use the rule where you add 1 to the power and you divide and so on and simplify. So there's our answer for the first one. This one takes a little bit of algebra to get to the point where we can work it. Take this fraction up here and split it up, divide, and then from this point I would work it like that first problem, getting this answer. Depending on where you're doing this, or if you're using online homework or something like that, you might need to factor it this way, okay? But those are the same. This one, u substitution, let u be 5 plus 9 over t. If you let that be u, then this part works out fairly nicely to be the du. All right, make the substitution, use a fairly simple rule, and then we get here. Okay, all right, so this one, another u substitution problem. When you read it, it says cosine to the 8th power of 6x, then sine of 6x dx. It'd probably be better to look at it this way, just to emphasize that it's the cosine of the angle is what's getting the power. You see the order of operations there? You take the cosine of the angle, you know, whatever that number is, and you raise that to the 8th power anyway. So that's u substitution. It ends up being a u to the 8th du. You want to see this part as the u. Why is that? What if you let u be cosine of 6x? This part works out to be the du. When you do u substitution, the objective is to take what you have there and substitute u and du. So with those here, those substitutions, I can get that to happen. I get to this point, and then the rule is fairly easy to use from there. I get this final answer. Okay. What about this one? If this one has some resemblance to that one up there, it's a different form though. This form here is u to a power, and that's the rule that we use in that case. We add 1 to the power and we divide. This is going to be cosine of u. So I'll let u be 6x. Du over 6 is dx. I'll make the substitution like that. And what's the antiderivative of cosine u? It's sine u. So with all u substitutions, the objective is to get it to this point where the rule is fairly simple. Okay? Anyway, so there's our answer for that one. Okay, so this one here is a kind of an unconventional u substitution problem, but it's still u substitution. All right? So this thing with the power, x plus 6, let's try letting that be the u. And the du is dx. That doesn't account for everything. That would be u to the 1/2 power and then du. But what about that x? I've got to substitute that away too. Well, if u is x plus 6, then x is u minus 6. So everything goes in right here. Remember, when we do u substitution, the objective is to completely substitute away the x in terms of u. Here I have a problem entirely in terms of x. I turn it into another one that's easier to work, that's entirely in terms of a different variable u. So when I get there, a little bit of algebra is in order. I multiply it together, and then the rule is fairly simple from there. I get this. Once again, depending on where you're doing this or who's asking you to do it or how strict they are, you could factor this that way. All right? Okay, but I said I was going to go through this fairly quickly so that you can see some problems and solutions real fast. What about this one? Let's break this one down into have and want. You have the second derivative of a function. You know that when you plug in -1 into the derivative, you get -3. And then you know that when you plug in 2 to the original function, you get 9. So it's like there's this function, all right? Its second derivative is 3x squared. If you found its derivative, you'd put -1 in, you get -3 out. And then for this function, if you put 2 in, you get 9 out, all right? So you have all that and you want this. How do we do that? Well, if I have f double prime, the antiderivative of f double prime is f prime. And I can work that out to be this, x to the third plus some constant c1. But I was told that if I put -1 in f prime, I get -3. So, well, okay, we put -1 in what I found to be f prime and say we get -3. That's enough information to solve for that constant c1. c1's -2. So f prime is x to the third power minus 2. Now I want to go all the way back to f. All right, so let's see. The antiderivative of f prime is f. So I do that. Again, I get a constant, as we always get that constant of integration. And okay, so there's the constant. And I was told that if I put 2 into the function f, I get 9 back out. So, all right, 9 out and 2 in. And that's enough information to solve for the constant c2. And I get c2 to be 9. And so my final answer for this function, x to the fourth power over 4 minus 2x plus 9. Okay. So question 8 turns out to be another u substitution problem. Okay. This time, let's see, it's going to be sine u du. Yeah, we want u to be 6x squared. That x dx, we can incorporate that to be the du. So u is 6x squared, du is 12x dx. Divide that 12 out, you got x dx. Okay, everything goes in like that. Rule's pretty simple from there. Final answer. Okay. All right, so here, this will be another have and want question. I think the one before this one. So question 9 turns out to be like that. So you have f prime is -2x root 8 minus x squared. And say that you have the graph of this function f or something. And there's this point on the graph that if x is 2, y is 6. So there's this function f. If I find its derivative, it's this. And if I take this function, I plug 2 in for x, I get 6 for y. So that really is, it's like question 7 I was just showing you a minute ago. So, okay, how are we going to find this? Well, the antiderivative of f prime is f. So how would you do that? Well, that's u substitution. Okay. So we'll end up with this for f through doing u substitution. All right, and I said the video was going to be quick, so I won't explain in laborious detail how u substitution works, but you'll get this with that constant of integration. All right. Okay, now I know about this function f, that if you put 2 for x, you get 6 for y. So I'll put 2 for x, I'll get 6 for y, and I'll solve for that constant of integration. So solve, 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 ends up being 2/3. Final answer then, 2/3, 8 minus x squared 3/2 power, plus c, will c end up being 2/3. Okay. Let's look at question 10. Question 10. Calculate the Riemann sum for a curve x squared plus 3x on the interval from 0 to 8. And whenever we calculate a Riemann sum, we're given a partition and sample points. Partition 0, 1, 3, 7, 8. Sample points 1, 2, 4, 8. Okay. Well, calculating a Riemann sum is fairly straightforward. Okay. 1 minus 0, and then we put that sample point into the function. Okay. And then 3 minus 1, and then we put this sample point into that function. So you could just do that and not even think about it if you wanted to. All right. Doing the math on the Riemann sum is fairly straightforward. You'll get 224. That's your answer. I'll say a little bit about the bigger context. All right. What is all this stuff? When you do 1 minus 0 and put that sample point in, and then you do 3 minus 1, and you put this next sample point in. What is that? Well, that's, you could imagine like this. There's this curve, and I'm looking at it from 0 to 8, and I've labeled off my partition elements and my sample points, and all you're doing when you do this is calculating the area of these 4 rectangles. That's what the partition and sample points create, all right? So yeah, what is this? Well, that number turns out to be the width of this second rectangle, and that other number there turns out to be its height. All right, and the width times the height's the area. So the Riemann sum gives the total area of those rectangles. If you wanted to think of it like that because it made it easier to remember and easier to do, go for it. But the calculation is fairly straightforward on its own. Okay? All right, so yes, there's the big picture. The Riemann sum is trying to measure the area under that curve from 0 to 8. Ultimately, that's what it's trying to do. These 4 rectangles don't do a very good job, though. They don't fit very well. But if you had more, they would fit a lot better, and you'd get a much better approximation to the area in that space. Okay? All right. 11, evaluate the definite integral. Okay, negative 6 to 6 root 36 minus x squared dx. All right, so it turns out to be 18 pi. And the way we do this one is not by u substitution. This is not the kind of problem that can be done by u substitution. So in the videos I had made for this topic and this kind of problem, I had explained how we'll use geometry to do this. You could think of this integral as measuring the area under that curve from negative 6 to 6 along the x-axis. Okay? Well, this curve happens to be a semicircle of radius 6. That's just what it is. And so this integral is wanting to measure, or the answer to this integral is the measurement of how much area is right there. Under that curve, y is 36 minus x squared from negative 6 to 6. Well, that would be half of a circle that has a radius of 6. That's 18 pi. Therefore, your answer here is 18 pi. Okay? All right. Question 12. We can do this one the same way. Okay, evaluate the definite integral. Turns out it's 25. All right. But we can solve by geometry also. You can look at this as the area under that curve. Y is 5 minus absolute value of x from negative 5 to 5. Okay, where I see that there's 2 triangles with base 5, height 5. So I did 2 times 1/2 base times height. I get 25. That's why the answer is 25. So you can do it that way. There's another way that I'll mention. You wouldn't be obligated to do it this way. But I guess the reason we do this by geometry is because I don't readily have a way to get the antiderivative of 5 minus absolute value of x. It's sort of like with this one here. That's not something that we learn to find the antiderivative of in Calculus 1. That's why I use geometry to answer this question. All right. This one, though, I guess is within reach of Calculus 1. As far as the antiderivative goes, we could do it like this. You see this absolute value curve. It's actually a piecewise function. Here's a line, and here's a line. This line, based on the points on it, is y is equal to 5 plus x if x is less than 0. This line is y is equal to 5 minus x if x is more than 0. Well, that's the whole thing right here. This piecewise function is the whole thing. So we could break this integral apart into negative 5 to 0 for this one and 0 to 5 for this one. And then work them. I mean, now that, making this a piecewise function eliminates the absolute value, the antiderivative is easy to find in that case. We get 25. We get the same answer, of course. Okay, so you could do it that way too. And it wouldn't really matter to me. Both techniques are within reach of Calculus 1. All right. Okay, so that's 12. See, 13. I can look at 13 the same way. The definite integral from 0 to 7, absolute 2x minus 7 dx. Well, that would be the area under this curve from 0 to 7. All right. And I see triangles. I see two triangles that have a base of 3.5 and a height of 7, 2 1/2 base times height. I'll get 24.5. Just like the other one, though, I could see this as a piecewise function, eliminating the absolute value. This line right here is 7 minus 2x if x is less than 3.5. And this line here is 2x minus 7 if x is more than 3.5. So that integral 0 to 7 is 0 to 3.5, 7 minus 2x, plus 3.5 to 7, 2x minus 7. Work both of those on their own, add them together, you still get 24.5. All right? Okay, so that's question 13. Question 14 involves some, you're forced to do this one by knowing some rules. There's really no other way. But if I'm given these integrals, 0 to 5 f of x dx is 15, and 5 to 7 f of x dx is 8, could I figure out 0 to 7? Well, isn't the whole the sum of the parts? See how this one picks up where that one leaves off? That's the same principle, in fact, of this last problem here. I wanted the integral from -5 to 5. Well, I could go from -5 to 0 as long as I pick back up at 0 and go all the way to 5. The functions are different depending on which side of 0 you're on, but the whole is the sum of the parts. You can look at it that way. So that's what is going on with that one. Okay. With this one, if we reverse the limits of integration, it will give us a factor of -1. So 5 to 0. Well, I don't have 5 to 0 up there. I got 0 to 5, though. So if you switch these limits of integration, you'll get this factor of -1. That's one of our rules for definite integral. So you'll get the opposite of whatever the answer to that was, which was 15. If the upper and lower limit of integration are equal, the definite integral will be 0. And we can factor a constant out of a definite integral or an indefinite integral. Okay, so this is 2 times whatever the integral from 0 to 5 f x dx is. Oh, you told me that's 15, so it's 2 times 15 is 30. Okay, 14. 15 was similar. All right, same sorts of rules, but we can split up addition in a definite or indefinite integral. Okay, so I work these on their own. I can split up subtraction, and I can factor out constants. All right. Okay, so that's all that was going on there. And let's look at this one. So this question, say it's presented, it's given as a picture, and it says, can you calculate this area? And say it's shaded and everything like that. And you look at it and you say, well, the curve is y is equal to sine x, and where you want to go from 0 to pi over 2 and find that area, well, that would be this definite integral. The definite integral from 0 to pi over 2 sine x dx. That will measure this area right here. It will do that. Okay. So in general, can you work a definite integral? Well, you find the antiderivative. In this case, it's negative cosine. You put in the upper limit of integration minus, and you put in the lower limit of integration, and you get 1. So there's 1 square unit of area right there. That's as big as a 1 by 1 square. That's how much space there is. Okay? All right, 16, 17. Say this one is given by description. It says calculate the area bounded by this curve, this line, and that line. So I labeled all that in red. Here's the curve. X is 2 is a vertical line. X is 0 is a vertical line. Y is 0 is a horizontal line. The space contained by those 4 things is right here. Okay. Well, if you wanted to measure the area there, that would just be this definite integral. The definite integral from 0 to 2, 5x squared plus 5 dx. Which, once you get it set up, is fairly easy to work. Okay. All right. So 18. Okay, so the way that this one's worded is it says at 1 p.m. and like 1 p.m. is supposed to be the initial time or the start time, the time when T is equal to 0. Oil begins to leak from a tank at a rate of R is equal to 6 plus 0.8 T gallons per hour. So we understand this function as you tell me a time and a moment in time, and this tells you how fast the oil is leaking out of the tank at that time. Okay, so it says calculate the oil leaked from the period of time from 1 p.m. to 4 p.m. Okay, now, 1 p.m. and 4 p.m., those are times on the clock. Those are not necessarily the times you do math with. I mean, what if we were using military time? I mean, there's lots of ways to tell time. The significance of these numbers is that 1 p.m. is time T is equal to 0. Oil begins to leak. Okay, so that means like if I put a 0 for T, that at that moment when it begins to leak, it's leaking at 6 gallons per hour. So 1 p.m. corresponds to T being 0, and 4 p.m. is 3 hours later. T is 3. So, okay, this integral will calculate the amount of oil leaked during that period of time. And what the integrals do in this case is they go from having information about how fast the leak is in gallons per hour to how much has leaked over that period of time in gallons. Okay, so we set it up. It's a fairly simple integral to work. So we get 21.6 gallons. Okay, all right, calculate the amount of oil leaked from 4 to 7 p.m. Well, okay, I just have to adjust the times. When at 4 p.m. on the clock, that corresponds to the value of T being 3, and 7 p.m. is T being 6. That's 3 hours later. And so that's the amount of oil that's leaked during that period of time. Why does more leak? Let's see. That's 3 hours. That's 3 hours. How come more oil leaks out during this 3-hour window than that 3-hour window? The reason why that's a bigger number and more has leaked out of the tank during this 3-hour window is because the nature of that function is the leak is accelerating, it's speeding up. The larger the value of T is, the bigger this number is, signifying how fast the oil is leaking. Okay, so yeah, that's bigger because in that window the leak was generally faster than in this one. Okay, so that's 18. Let's see, 19. This is a question where we go from speed to distance. It says an object moves along the number line. I get its velocity, v of t, is t squared minus t minus 90. The clock runs from 1 to 15. So first part of the question, calculate the displacement. Well, the displacement will just be the integral from 1 to 15 of the velocity dt. That's what it is, okay? So that, maybe the calculations would be difficult if you didn't have a calculator, but it's a fairly easy integral to do with the help of a calculator for the numbers. And you'll get negative 742 over 3. That rounds out to be about 247 or so. So displacement, well, what that means is that at t is equal to 15, at that end time, you'll be about 247.3 units left of where you started. Okay, so you'll start somewhere at t is 1. By the time t is 15, you're left of your starting position by that much. That's what we mean by displacement. Part B says calculate the distance. Now that's something totally different. Because if you start somewhere and you go away and you end up back where you started, your displacement is 0, but your distance is obviously not 0. So how do you calculate the distance? Well, the technique there is I need to divide this motion up into left versus right. If that's the velocity, if the velocity was negative, you would be moving left. If the velocity was ever positive, you'd be moving right. I need to divide that up, figure out when I'm moving left, when I'm moving right, okay? So now this would have been covered in another video, but you set this equal to 0, you figure out when the velocity is 0, that turns out to be 10 when you're stopped, and then you solve that by factoring, you get that number. So t is 10, okay, v is going to be 0. And then with test values, you can figure out that when t is less than 10, the velocity is negative, we're moving left. When t is more than 10, it's positive, we're moving right. Okay, so we're moving leftward up until the time t is equal to 10, where we gradually slow down and stop, and then turn around and move rightward. So each of these integrals will calculate the individual distances left and right. This is the leftward distance. It's from 1 to 10. You'll get a negative number because that's left, all right? In the rightward distance, that's from 10 to 15. You'll get a positive number, okay? Well, the absolute distance that you moved would be your leftward plus your rightward. Now, I know that's negative, signifying that it was motion this way, but to get my absolute distance, I'll take that number, 526.5, and add to this one. That will be my total distance, okay? 2417 over 3. All right, one last question. Let's recognize when to use Lhopitals rule. This limit, if I tried to do it by substituting 9, would give me what's called an indeterminate form, 0 over 0. That's the situation we could use Lhopitals rule. Lhopitals rule says I can take the derivatives of each individual part of that, the numerator and denominator, and then reevaluate the limit. Well, that's easy to do. Derivative of 5x minus 9 is 5, and x squared minus 81 is 2x. I put 9 in, I get 5 over 18. So there's your limit. Okay, so what we got there, 20 assorted questions for the last test for Calculus 1.